Okay, so we're starting to talk about special relativity, and of course this is Einstein's most famous theory. Um, Einstein was an interesting cat himself. He was not a great student. Obviously, he was brilliant, but was fairly bored and not very satisfied with his schooling. He was German, and he did come over to the United States before the war. Was not happy with Hitler's ideals and came as a political refugee, so to speak, to the United States. Several professorships, several publishings onward and upward, and he also was on the Manhattan Project, which eventually made the bomb that ended the Second War. Special relativity. We all know that motion is relative, so as we look at motion of any object, we take a ball, and that ball is going in this direction. If we are on the outside looking in, that ball appears to be moving to the right, in this case, at 10 meters per second. That's from the outside looking in. Well, if we happen to be in a boat and we're standing watching that ball and we're on the boat and that ball is thrown at 10 meters per second and we are moving at 5 meters per second, the ball moves at 10 meters per second to the person on the boat, but to a person on the outside looking in, it would move at 15 meters per second. And this is true for all of our objects that we've studied so far. The one thing it's not true for is light. If I have a flashlight that is shining light in this direction, regardless of how fast that flashlight is moving, that light has a constant speed of c. And c is 3 times 10 to the 8th meters per second. That is the speed of light. And it doesn't matter how fast and in what direction the sender or the receiver, in this case an eyeball, gets that light. It doesn't matter. Light does not respond like other things do with the velocity of the sender or the receiver. So, think about this. You're down on Earth and you're watching this. There is a spaceship. Okay? And the spaceship has a clock on it. And it's a special clock. It is a light clock. And the light clock has a mirror here and here, and it bounces light back and forth. Now, light is not magical. It still takes time for light to get from one point to another when you're not actually a particle of light. So let's say that this little trip in this spaceship takes, to go forward and back, takes 0.1 seconds. And that's fine for a person on the spaceship watching. But what about this person on the ground? Because this spaceship is moving, what happens is the mirror starts here, but by the time it's time for the light to go up, the mirror is here, then the mirror is here. Well, this time observed by this person takes 0.2 seconds. So afterwards, this person right here and this person right here have a talk. And they say, how fast is your light clock? I mean, it's 0.1 seconds according to the spaceman, but the person on Earth says, no, it's not. It's 0.2 2 seconds. And this is because this light does not change speed when it's moving. Now, Einstein knew this. How? We don't know, but he did know it. And he said two things. He said, space and time are on a continuum. So we have a continuum, and I like to draw it like a ruler with space, time. There is no such thing as space. There is no such thing as time. It is one quantity called space-time. And if you think of them as two containers, in a way, that they are always at a level that is constant. So this is the time, and this is the space. So someone is standing still. They're going through time. They're not going through space. What would that look like? Well, if somebody's not moving through space at all, their space bucket would be empty, or pretty empty. Their time bucket would be really full, because the two buckets together have to add to a constant. Well, what happens if we're moving really fast? Well, the space bucket fills up because we're going through a lot of space, and the time bucket becomes less for the person traveling. So, some equations. And Einstein has a relativistic term, and he says this relativistic term happens all the time. Now, we don't use it in our calculations because it's so small, but he says the time for someone moving at all, and this could be on Earth or anywhere, reacts to this equation. And this equation is v squared over c squared. And let's talk about this for a second. Okay? This term, v squared over c squared. This is the velocity that the person's moving. This is the speed of light. So when we're talking about a c that is actually 3 times 10 to the 8th, that's 3 and 8 zeros, and you square that number, okay, that's a big number, right? We're talking about 9 times 10 to the 16th. So we have to go very, very fast, or very close to the speed of light, because if this number is small, then that number divided by this big number is just basically 0, 0.0000000, and 1 minus a very small number is 1, and the square root of 1 is 1. So the time of our traveler and the time that we observe on Earth is the same. But if v gets to be, let's say, 50% of the speed of light, all of a sudden our time of our observer is getting multiplied by 1 minus, let's say it's 1 minus 0.5. What's the square root of 0.5? 0.25? So all of a sudden, we have a very small number, or a small number, 1 minus a small number, times t. So if this term right here, 1 minus v squared over c squared, if it equals, we work that out and somebody's traveling, it equals 0.5. When you look at our equation, oops, I want to get an eraser on that. 1 times 0.5. So now, if we spend 10 years, Earth time and space, we would spend 5 years for the spaceman. Okay? So time is not a constant. He also did some work with length. Length, very similarly, contracts. So if you're going to travel a really long distance and you go very fast, the length that you actually travel would be much less than it actually is as observed on the Earth. So this would be a great trick with a used car. You could drive a used car almost the speed of light and record very little on the odometer because the length has changed. So when we talk about traveling to distant, faraway stars, we may not have to travel that far because the length's going to contract if we can go very fast. He also talked about mass, and mass also increases, or changes, excuse me, but look where the equation, where the relativistic factor is now. Now we're going to be dividing by a very small number. If we get close to the speed of light, this number is going to be very, very small. When you divide by a very, very small number, this gets very, very big. This is the reason we can never go the speed of light, because our mass increases eventually to infinity, which would require all the energy in the universe to get any point of mass to the speed of light. So these three equations, the time equation, the length equation, and the mass equation, are what we're going to talk about and start using in class tomorrow. And I just want you to watch this, and I want you to keep track of where we're going with this, and it is a lot of fun, and we're going to think about what kind of problems that we can solve using these equations tomorrow.